at Kinetica, we've been purpose-built from the beginning to kind of solve this problem of how do you do complex analysis while data is coming in. That was the problem we were built to solve. And we call that whole problem set the active analytic problem. And the best way to describe active analytics is to juxtapose it to passive, where passive is, reports that are 24 hours old. Passive is reports that are generated in a batch fashion. Active is continuously incoming data, analytics that are continuously updating, triggers and rules that are continuously being evaluated against those updated metrics. So we feel strongly, and we're seeing traction in the marketplace around this need for what we can do as an active analytic platform to drive next generation application development and drive AI lifecycle. And at the end of the day, and my boss, Paul, always, after I get very nerdy, he always says it's really just about business outcomes and being able to drive, the next, exponential step in what enterprise is trying to do around efficiencies, around innovation, around being able to use data as the business. So, we're being used for network planning, we're being used for, autonomous, we're being used for real-time risk, customer 360. So, you can see customers definitely identifying the need for this. And, in the past 20 years, you've gone from using bespoke solutions and trying to tie those together and realizing that that's not a sustainable path to something like Kinetica, where we've thoughtfully built from the ground up a platform that can really drive, this problem set. So fundamentally, we've broken it down into, kind of 4 key compute disciplines. So streaming analytics, when I say streaming analytics, everyone says, oh, that's been solved already. But when I say streaming, I'm not saying a fixed window of data being analyzed, and I'm not talking about fixed partitions and fixed aggregates. Those approaches no longer qualify because they're not sustainable. As you want to do more complexity, you want to analyze, across partitions, you want to do new aggregates, it's just not sustainable from an operational perspective to go with the kind of bespoke solutions of the past. The historical analytics, is kind of table stakes. You need to be able to do very complex OLAP at massive scale to be able to drive next generation application development while data is coming in. So the streaming and the historical are really one thing. And finally, as you think about data processing, location has been something that's just really been ignored for decades and now is becoming the key correlative element that drives insight for people, because now there's so much location data being generated and allowing linkages of behavior to be found. And finally, giving a operational fabric to ML-powered analytics. And so when I say that, what do I mean? I mean giving a way for your data scientists to access your operational data in an operational way. I mean giving a inference fabric that you can easily deploy to and have production level visibility into your model as it's running. Being a data platform, we're actually able to give what I call a data-first operational framework, where we're actually capturing and heavily modeling the data elements that are a part of the ML lifecycle and all the data interactions. And we'll actually show you what we mean in my portion of the demo. So given all that, we were able to team up with SFEI and think about how can we leverage Kinetica to accelerate the work that, the incredible work that they're doing. And what Tony is going to cover and Lorenzo is going to cover is exactly how they use Kinetica to power, their future footing and where they're going.
Research is showing that we are ingesting plastic on a daily basis. By intercepting trash before it makes its way into the bay, we are preventing microplastics from getting ingested by other animals and in turn by people. The San Francisco Estuary Institute, along with our close partner, the Southern California Coastal Water Research Project, has been funded by a public agency, the California Ocean Protection Council. Conventional trash assessments require a crew of up to 10 practitioners in the field. Practitioners are in the creeks, in the streams, identifying trash, classifying trash, counting it, weighing it. With a drone-based method, you're able to collect thousands of images and then feed that into a machine learning algorithm to detect the trash. Without Kinetica, The machine learning algorithm that would detect trash might take days. But with Kinetica, we are able to run the same detection methods in hours.
When they run that model in Oracle Cloud, they're able to access what we call a GPU, a graphical processing unit. So this allows them to run the model inexpensively and very fast.
Realizing AI's potential will not translate naturally to societal benefit. So we really need stakeholders such as companies, NGOs, governments to come together to shape the way we think about AI deployment and ensure that the outcome is what we want.
We are at the forefront of action, but we have to be backed by the right information. And that's where institutions like SFEI come into place. Having a more systemic way of monitoring trash, that's a remarkable resource that cities, that different organizations can use. We do have the power to make positive change. We know that we can restore wetlands. We know that we can add urban greening features that can filter our water. It can really help our wildlife to thrive, our people to enjoy nature, and bring life back to areas which are otherwise barren. Particularly in the Bay Area, we have so many people who are willing to take action once they have information. But I think once we understand the impact, then we are, as a culture, willing to take bold moves. I think I have a mic here. I just need the clicker. There we go. Well, hello, everyone. So I'm Tony Hale. I am with the San Francisco Estuary Institute, as you may have picked up from the video. And just want to thank Nima for not only for including us in this presentation, but also for the fruitful partnership that we've experienced. When you look at this picture, what do you see? You know, you might kind of look out there and see, let's see, does this work? Yeah. You might pick up on the heron, right? You might see a beautiful channel, the native Spartina that's growing here. You might look off in the distance and see some structures. This is a marsh at the edge of the bay, at the edge of the San Francisco Bay. And what you don't see in this picture is something that's there, which is trash. And you might say, well, I don't see it. And what's unique about trash as a pollutant is that it is something you can normally see, right? Unlike mercury and copper and chemicals that we do worry about, and the San Francisco Estuary Institute worries about it. Trash is unique. It's something you can see. You can see it visually and take action. And so sometimes it takes a different view. So this is a marsh looking down, what's called the nadir view from aerial imagery. And when you're looking at the same marsh from that oblique angle of the landscape view, being on the terrestrial side of things, you don't necessarily see what you can see here. So we got, you know, this structure sitting out there that might be behind this berm. You got different pieces of things. So being able to fly a drone and get a view of the landscape, it opens up a whole new world of possibilities. And the organization I work for, the San Francisco Estuary Institute, I'm going to stand over here so I don't get feedback. I'm trying to get in between the projector and the speaker. But you know, we work in water quality, which is inclusive of administering things like a regional monitoring program for water quality in San Francisco Bay, as well as trying to optimize wetland restoration efforts through things like historical ecology. But really what it comes down to is giving people information, which includes a whole range of stakeholders, from policymakers to politicians to agencies to community-based scientists, but giving them information so that they can take action, so that they can help to revitalize nature in their communities. And part of that is to help validate some trash monitoring methods that are currently in use. So we were contracted by the California Ocean Protection Council in partnership with a group called the Southern California Coastal Water Research Project. Say that 10 times fast. They are our partners on a project that is seeking to validate those trash monitoring methods with the idea that people are out there monitoring trash all the time. You have people doing coastal cleanups and really taking some significant steps forward. But everyone's doing things in different ways. Some people are counting the individual pieces. Some people are weighing the trash, measuring volume, doing all this kind of stuff. So what we were brought in to do is to kind of see if we can set some standards, right? Looking at accuracy, looking at precision, looking at the cost and practicality, as well as trying to map these things to management and research questions. But the problem with looking at those currently available trash monitoring methods is that they are very time intensive. So you got a tally sheet here, and people are out there, sometimes spending anywhere from an hour to an entire day. Those of you who've been out there on doing your good work to clean up trash, you know what I'm talking about. So it can be very time intensive. It's also very labor intensive. It might be anywhere from just 2 people to a team of tens of people out there counting trash, cataloging it. So it takes a lot of work. It's geographically limited, right? So where you go is rare, determined by certain geographic constraints. Where you can go. So take, for instance, the marsh that you saw as my first picture there. That's a sensitive habitat. You just can't traipse through there without destroying it. So there are limitations to where you can go. And those time constraints, labor constraints, it means that you can't get out there very often. So some cities, some stormwater management programs will only get out there twice a year to determine how often, how much trash is out there. And what that means is that you have temporal limitations. So the image of how much trash is making its way into our bays, into our creeks and bays and then oceans, it's made up of just a few data points, right? You just don't have the temporal density that you need in order to determine, is the problem getting better or worse? When you put in a trash ban or a plastic straw ban, does that have a positive effect? Are you seeing the results you need to see? So what we wanted to do is, in addition to the regular trash monitoring methods where people are out there, as you saw from the video, in waders and kind of picking up trash and counting it, we wanted to try something different. We wanted to kind of break from the mold, which meant flying drones over creeks and rivers where you're allowed to fly, and in these public right-of-ways, and seeing what kind of imagery we could collect to help inform the picture of overall trash load. And so we wanted to extend the temporal and spatial possibilities and also do so in a way that's accurate and precise. And so part of it is to determine practicality, right? To see if a method that is deployed in this way is fundamentally sound and if it is viable. And our partnership with Kinetica really helped us to get around our own technological hardware limitations, let's say, so that we could get out of our own way to make sure that the measurement of viability wasn't just tied to our own short-term limitations, right? And so figuring out what are the circumstances when you can use UAS. And believe me, we ran into many constraints where you can't. You can't fly near airports. You can't fly over houses. You can't fly over people, domiciles, etc. If you tried to fly a drone just over this building, you'd be banned from doing that. And you'd probably be arrested and hauled away. So don't try it. So there are plenty of restrictions. So where can you do this? And where can you pair this new way of looking at the landscape with more traditional ones? And so in addition to capturing the imagery, though, we thought, let's actually use machine learning to read the imagery and get towards that active stance that you heard Nima talking about earlier, right? So that rather than kind of just extending the field work from the field to a desk where you're counting trash by looking at imagery, can we start developing a model that would detect it automatically? And so the advantage we have is that we have a measure of truth because we're out in the field, we are deploying these regular trash methods where we're doing those counts, and we're able to see if the machine learning method is comparable in terms of accuracy and precision. So this is a traditional kind of a subset that's used in an ecological framework. It's called a quadrat, and you inventory everything that you would find in those four areas. And you can kind of like see the details of different things. So this is an image taken from a drone at a certain altitude of 60 feet. And this is another image where, you know, that was a staged image. This is an actual, the way we found it. And this is annotation to mark all of the different pieces of trash. And trash is a little hard. It's not like dogs and cats where, you know, there's certain kind of morphology that's consistent. This is, you know, trash is like a weed. It's anything that shouldn't be where it is. So it's a little hard, but we've been annotating trash in these environments with the idea of using that to train the model. And so when we zoom in, we can see that, gosh, it goes on forever. We have tons of trash, and we have thousands of pieces here. So I'm going to now turn over the mic to Lorenzo. Lorenzo Flores is one of my web application developers who's going to talk to you about some of the details of the model.
Hi, good evening there, everybody. Thank you, Tony. So I'm just going to run through some of the basic numbers of our data set and speak to a little bit to the process that we've taken towards training our model. And I say our model because, as you'll notice here, let's see, is this the... no, the pointer, is that right there? Yeah, so as you notice here, our hardware constraints, as Tony was pointing out, our modest hardware constraints. So this is actually my workstation at work, our Dell XPS 8700 with the Core i7, 32 gigabytes of RAM, and then you know, just a traditional consumer end, middle tier of past generation graphics card. So you know, it's just even sort of starting this work was very challenging and getting to a point where we could see if it's even viable. As you'll see here, our library of images. So this is basically the data set that we've collected using drone technology, as Tony pointed out. We have 422 UAV-based images, and they're quite large. So this 5,456 by 3,632 pixels. Given our constraints here, we quickly found that we need to crop that down. So we had to go ahead and go through and crop that to about 30,000 images. Each of those is a little over 600 pixels by 400 pixels. I can give definite numbers later if anyone's curious. This number comes in. This is important, and actually in the next coming slides, where we show a benchmark that we've been able to do to compare the to basically show the improvement gains that we get when we transfer our machine learning model to Kinetica systems. But I do want to call out that of the 30,000 cropped images, we basically have 30,000 annotations spread throughout, and so that's where within this drone imagery, there's a lot of regions where you may not have trash, but then there's regions where they're very dense. And I think it's important to say, like, we had staff, an intern come and very excitedly help us to do this annotation work, and it's pretty gnarly. So we're gonna get to the sort of the improvement gains that we get by leveraging Kinetica systems. So we went ahead and said, okay, how can we even see like what if this works, how it's gonna work, what kind of processing decrease in time we can get. And so we basically did a slight run here. So on our system, because it's fairly low powered, we didn't actually run this experiment of running it for the 17.4 days to do inferencing. So let me actually put a little context here. So we went ahead and took our model and we said, okay, well, we're basically using all of our survey imagery as the training set. So just to get an idea of how quickly we can go through and inference over this a large data set, let's just take that training set and inference over those 30,000 cropped images. And so we just did a few data points, and the average was about 50 seconds per inference. And so we're simulating continuous inferencing, which means that we're basically, how long does it take to load the model into memory, inference over an image, and then write the output. And so that basically translates into about this 17.4 days of processing time that it would take us just, with my workstation spinning on that. So Kinetica went ahead and said, okay, let's take that model that we'd been training and see what they could do with a single NVIDIA K80. And so they were able to actually go through that same processing and actually go through the inferencing in 5 days' time, which was like, wow, that's awesome. That's way better than what we can do. And then they said, okay, how do we scale that even further? So they went ahead and provisioned the 8 NVIDIA V100s, so distributed GPUs. They were able to get that processing time down to 18 hours. So I think what's really important here is that sort of makes this within the realm of viability of, hey, if we go ahead and we can invest the effort and time tuning this model so that we can eventually start actually using it to identify trash. I think that's, that was a really important thing for us to be able to get through, because up until this point, we've been just trying to figure out if it's viable. So I think we're moving on to, oh, that's right. I'm sorry. Thank you, Tony. So this actually, I think I just kind of contextualized this. This is just to call out in visual form the numbers of the hours for compute time that I went ahead and was describing in the previous slides. So we've got that 417 hours down with our SFEI baseline, my single workstation, down to 120 hours with Kinetica single GPU, down to 18 hours with the distributed GPU. So I mean, this does put in full glory the performance improvements that we're able to obtain. So here we go. Thank you.
All right. So one quick thing. So this also is, something that when you deploy your model inside of Kinetica, you get for free. You get real-time visibility into how your model is inferencing, giving you complete, BI level analysis capability to understand your model's behavior in real time as it inferences. And you can actually monitor each inference and dig into each inference if you want it. So starting Friday, we're very excited about, what we're doing with Rapids. And so Friday we'll be putting out our next version of Active Analytics Workbench that will be showing the, complete end-to-end integration with Rapids, showing off our managed lab workspace capability. And the idea here is to, really bring out what makes Rapids so special, which is, empowering the data scientists, allowing them to collapse training times, allowing them to do, easy data exploration, and put that atop Kinetica's data warehousing capability, right? Giving them access to the operational data in an operational way, and giving them an easy way to, once they've made that model with Rapids, deploy it operationally and easily. So this is our Active Analytics Workbench, right? And again, this is 709, which will be out on Friday in public repos. You can just go download it. And this is the Rapids Managed Workspace. So he's going to click Launch Session, and that's going to be launching a hosted, persistent Rapids Jupyter Lab, right? So everything on the left-hand side is persisted for each user, right? So, it's housed, it's, co-located to a GPU. It's all managed by Kinetica. All the connectors and Rapids libraries are all built in. Can I pause this? No. Okay. So what we're trying to do here, and I'm going to try to catch up to this video, is we're trying to build a better firewall. So in Kinetica, we actually have all of our router events being captured into a Kinetica. So the router has rules, right? And it tags, different data transfers as accepted or denied. So that first query we did was against a 4 billion record table that's getting ingested into constantly. And we said, hey, let's just show all of the denied events. And we can see that there was a hotspot in Amsterdam, right? So now we're going to, again, using Kinetica inside of our workspace, pull out, specifically the data as it was related to that Amsterdam hotspot, right? So we're trying to understand, okay, the router is and the firewall is flagging all this stuff as denied. Something's going on in Amsterdam. Let's see if we can pull out another feature that's, using this data as our kind of labeled data set as our ground truth. Let's see if we can pull out another feature that's of interest that we could leverage to build a smarter firewall, right? So pulling out that data, one of our engineers, Saif, had the idea of, let's see if we can find any outliers when we look at kind of event time, right? Can we find sufficient data as we do feature exploration, where event time might be a key indicator that we should make a feature. And so he ran that query again against a very large data set, pulled it into the lab, used standard Jupyter Lab libraries to do that chart, right? And he said, yeah, that is an interesting indicator. I'm going to add that to the feature set. So one of the things that Active Analytic Workbench does is fully model out all the features in your feature set. So that one little call there is actually going to be registering all the features that he's going to need for his model training, and we'll show you the actual features that got registered. So the only thing that we don't actually do in this video is run this training, but at this point we've hydrated our CUDF, and we're going to run an XGBoost binary classifier. We're not going to run it for the purpose of this video, but again, the outputs are those data files. These are just standard serialized models. You can see that they appear in your workspace, and if you close the workspace, come back to it, they're there. So this gives your data scientist team a complete end-to-end sophisticated way of housing their entire workspace. So what he did there is say, okay, I want to register this model with Workbench, right? So when he does that, we wrap it up in our container, right? And we, in this case, register it with Docker Hub. It can take any registry, and park that, and we'll come back to it. So we've registered our model, right? What we also want to do now is we want to evaluate our model, right? So what we do next is do a large batch inference using the new model against a sample data set, right? So he does that here, and we store all those inferences in that table. And he's going to show you the rapids inference speed, which is pretty impressive. And this is all running on a single V100. So that each workspace gets co-located to a single V100. From there, right, we've now captured all those inferences in that table. We're going to compare the inferences that model made to the same inferences that the firewall made for those same data records using this SQL, which is a join. And we're going to pull out all the records that we flagged as a denied event and that our firewall did not catch. So again, you can see here, oh, maybe we were onto something, because if as we dig in, we see that there's a whole bunch of events that our firewall didn't catch that we did in other areas, but in that hotspot area of Amsterdam, right? So, clearly, if we're using that location as a key indicator, clearly our firewall is missing some behaviors that our model caught, and that was all done in this workspace using your standard interaction model that your data scientists are going to be comfortable with. Everyone's comfortable with Jupyter Workbooks and Jupyter Lab, and this is built upon the standard Rapids container. So everything you're used to in your Rapids container is also available in that workspace. So we took that image that we registered, and now we're going to be deploying it. So when we hit inspect, all the features are fully modeled and tied to that model, right? And including the final output inference, right? So all the data elements that are part of this lifecycle are fully modeled, captured, referenceable, right? So from that import, we hit create, and now we're going to deploy this in a continuous fashion. So all the metadata around it is captured, and now we're going to do a click button deploy. So you can imagine your data scientist working in their Jupyter Lab, single API call, registering this, coming to a UI, and deploying this in a production style manner, right? So taking into account GPUs, right? Taking into account the data lifecycle and how you want to feed that model. So in this case, we're going to do a continuous, right? So the input records are going to land into a table in Kinetica, and all the inferences will be output in the table into Kinetica. So that allows you to do full BI style, model behavioral analysis in real time. So he's going to click deploy. So I told you it's real. It takes a little bit. So this deploys it into our K8 fabric, co-located with the GPU, right? And then that's all the metadata, right? So other data scientists can come and see deployed models, right? And click into the features and the details about what's being deployed. And now we're going to take a look at that output table that we described, right? So it's already got 1,000 inferences in it. And as you refresh, you can see it's scoring our network traffic live. And the interesting part is that we capture not only the output inference, but the exact input that was used to generate that inference. And through our audit tool, you can actually do a complete lineage, going back to the features, the feature transformations, and the original data that was used to train the model, and really give your operational teams an easy way to debug. Because I've seen a lot of teams where they're trying to understand a shift in model behavior. They don't remember what data sets were used for training, right? They're going back through and trying to understand, okay, well, did we use this version of the CSV or that version of the CSV? All that's captured, all that is, housed inside of Kinetica because, we have that data processing pedigree. And this is just kind of re-showing. So, he closed the session, now he's relaunched it. This particular workbook's here. Everything else that he generated in that session's here. It's how, the persist is completely housed in Kinetica, so you don't have to worry about losing anything. You don't have to worry about, your team's laptop GPUs, being powerful enough. It's all completely taken care of by this workspace.